YouTube. This is my last video on my module on exponential functions. But we're going to talk about radioactive decay, which is often something we discuss when we talk about exponential functions. But radioactive decay, interesting thing is this. Radioactive things tend to decay over time using exponential decay models. Okay, they don't decay at a linear rate. If I said, you know, I have a certain amount I'm starting with of exponential material or radioactive material, it doesn't go down like a certain amount each year. It actually decays over time. So it does this little ditty right here. And so that being said, we can model exponential decay or radioactive decay using exponential things. Okay, but specifically, let's go ahead and start with this. We're concerned with the amount of radioactive material that's left over an amount of time. We usually measure it in grams, but specifically, we talk about radioactive half-life. So a half-life of something, okay, it'd be like this. A half-life is the amount of time it takes for something to be cut in half. So if I were to put 6 Cokes in a college dormitory refrigerator, and I come back and I check on it every hour, it would be the amount of time it would take before people basically snuck away 3 of my Cokes, and that'd be its half-life, and then the other half-life would be, half of 3.5 is when there's 1.5 Cokes left. But of course, Cokes are discrete, so we won't go there. But anyways, that's the case. So what I want to do is I want to present a situation when we look at radioactive half-life. Okay, so we say let Q or Q of T, or represent the mass of radium-226. Okay, and we know the half-life of radium-226 to be 1620 years. But what I can tell you then is the quantity of radium present after T years is given by this equation, where I would be starting in this instance with 16 grams of radioactive material. I'll tell you this is the initial amount right here. Okay, so I can model it this way. What I want to do first of all is I want to sketch the graph of this on the interval from 0 years to 5,000 years. So starting with 0 years, let's go ahead and discuss this. This means my initial time. This is my initial time. This is right when I start with my radioactive material. So if we're going to sketch this, we said we want to sketch it over 5,000 years. Sorry for my crooked graph here. But we say 5,000 years. We've got 0 here. We'll put time down here, and we'll put the amount of radioactive material, Q, as a function of time up here. But we say after 1, 2, 3, 4, 5, we'll say this, and this is time, ooh, let's just get that out of there. It's driving me nuts. Time in years, and we say in thousands of years. Okay. So we've got this down here, so we say 1,000, 2,000, 3,000, 4,000, 5,000. We can model this, and I know that we started with an initial amount of 16. So if I say 1, 2, 3, 4, 5 grams, 6, 7, 8, 9, 10 grams, 11, 12, 13, 14, 15, 16. Here's what I know. We're starting off with an initial amount of 16 grams. Now I can show this. We can just plug these things in. I've already got the function. If I said, okay, at 0 years, how much radioactive material have we got? And so I get this 16 times a half to the power of 0 over 1620, which is the half-life there. But 0 over anything is 0, and anything to the power of 0 is 1, so I'd get this 16 times 1, and so I get 16. So at 0 years, we have an initial amount of 16 grams of this radioactive material. If I'm going to sketch the rest of this graph, let's just plug in 1, 2, 3, so on and so forth. We can do this just get my calculator out here. So in this model, essentially what I want us to see is we'll be taking 1/2 to the power of, T over 1620. So if I said 0.5 to the power of, now in this case, after 1 year, we'd say 1 divided by 1620, in parentheses, my exponent. And so that's 1/2 to the power of that times 16. So we'd say after 1 year, we'd have about 15.99 grams of this left. After 1,000 years, 1,000 years, we'd have 15.99 grams of this left. So we draw that in there. And then we say, okay, go back to my calculator, and this time we'll say 16 times 1/2, so we'd say 1/2, 0.5, to the power of, in parentheses this time, ooh, that's why there was so much left. I was like, wait a minute, time, I put in 1. Sorry, 1, 2, 3, 4. When in reality this is 1,000, 2,000, 3,000, and 4,000 and 5,000. I apologize to my audience. Let me just go ahead and show you the mistake that I just made. We'd have this 0.5 to the power of time divided by 1620, where we have 1,000 divided by 1620. I thought there was a disproportionate amount left. So we get that. So this is a half to the power of 1,000 divided by 1620, and we're going to take this times 16, which was our number out front. So we have 10.18 grams left. So looking up here, we'd say don't pay attention to this. About 10.18 grams, so it's decaying. After 2,000 years, getting the calculator back out, we'd say 0.5 to the power of, in parentheses, 2,000 divided by the 1620 that's over here in our exponent, in parenthesis, equals, and we'll take this times 16 equals, so about 6.8-ish. So at 2,000 years, we've got about 6.8-ish grams of material left, 6.8-ish. So I just want to sketch this here. We say, okay, so how about 3,000? So 0.5 to the power of, in parentheses, 3,000 divided by 1620, in parenthesis, equals times 16. So we get about 4.43 grams left. That'd be about right here, 4.43 grams. So you see it's kind of leveling out here. We've got a couple more to go. We say 0.5 to the power of, now we'll do 4,000 years after, 4,000 divided by the half-life, which is 1620, in parentheses, equals times 16. And we get this 2.89-ish. So after 4,000 years, we get about 2.8-ish, 9-ish grams of material left. And then after 5,000 years, so we got 0.5 to the power of, in parentheses, 5 grand divided by 1620, in parentheses, equals times the 16 we started with. Oops, let's make sure. Oh, no, this is not a bad thing. 1.88. Sorry, I get a little ahead of myself. So this is a good sketch of what our radioactive material is doing over time. It's decaying over this course of time. So I want to determine what the initial quantity was when time equals 0. Well, I just want to point this out. We already determined this initial quantity right here. I just wanted to reiterate the fact that anything to the 0 power is 1. So when I plug in a 0 there, I get a 1 here. And that's why we refer to this as the initial amount, because whenever you plug in 0, this part right here is going to collapse to 1. And so the initial amount would be this number out front. And then last but not least, we say determine the quantity present after 1,000 years. Well, we did this. We did this about 10 point something right there. So in terms of half-life, we could determine approximately the half-life. We could say, well, that's at 8 years. If I were to trace this out over here, if I had about 10.8-ish grams here, and then here I had about 6.78-ish grams here, we could speculate as to what this would be, but the half-life would be somewhere about right here. I'd have to guess about, I don't know, about 1,200 years, 1,300 years before it's cut in half. But yeah, this is a good example of a radioactive decay problem to get started with those.